In quantum mechanics, as in classical mechanics, there are actually relatively few problems that we can solve exactly. In quantum mechanics, we can look at the free particle, the particle in a box, the harmonic oscillator, the hydrogen atom, and a few others. Beyond such relatively ideal and simple problems, most others require that we take some approach, either with approximations or with purely numerical techniques that is not just an analytic one. In quantum mechanics, it's useful and important to look at approximation methods for two reasons. First, of course, such methods mean we may be able to calculate some useful results without too much difficulty. Secondly, though, in quantum mechanics, we can use approximation methods to help us conceptually understand many situations quantum mechanically. Often, approximation methods allow us to think of effects and processes in a meaningful way. For example, the interaction of ordinary light that we see around us with the materials that we see around us is in one sense a relatively weak interaction. The light does not really perturb the material very much. Only if we shine very strong laser light at materials does the light have much substantial effect on the material itself. As a result of this relative weakness of the interaction between materials and everyday light, it will turn out that we can use one particular kind of so-called perturbation theory, a kind of approximate model based on the idea that we're only making very small changes. We'll be able to use that approach to model such interactions quite conveniently and simply to a very high degree of accuracy. Such a model enables us to understand, for example, the colors of materials if we understand the basic quantum mechanics of the materials themselves, and gives us relatively simple formulas to work with. We'll come back to that particular kind of model, which is an example of a so-called time-dependent perturbation theory, in a few sections. We're going to start here first by looking at problems where the system is not really changing in time, but we are doing something specific to it. A good example is how an applied electric field, a voltage of some kind, changes the properties of some material or structure. We can imagine increasing the applied voltage and watching how our material or structure changes as a result. For example, the effect of an applied electric field on an atom is to change the precise frequencies of its atomic absorption or emission lines, something we know as the so-called Stark effect. Such effects are often handled quite well by approximation theories, again, because the perturbations we can make on an atom are relatively small with the kinds of fields that we can actually apply. Our fields are much smaller than the fields inside the atom itself in that case. Such an effect can be handled quite effectively by time-independent perturbation theory, which is in the end a fairly simple series of successive approximations. And we will look at that approach as a simple version for such a problem. So, for a problem such as applying an electric field, there are several other approximate techniques and approaches we could take, some of which, such as the use of finite matrices, for example, conveniently enable us to model quite strong perturbations of the systems. Other techniques, such as the variational method and the tight binding method, can give us significant physical insight into the behavior of some quantum mechanical systems, as well as giving us useful approximate answers. So here we're going to introduce various of these techniques that are part of the everyday toolkit of any good quantum mechanic.